C-I-E-I-O. All right. So if you took care of the notes for section 3 was on the topic of orthogonality. In other words, it's kind of a new name for indicating that two things are perpendicular. In the case of perpendicular vectors, what orthogonality means for us is that if we had two vectors u and v, we could form their dot product, and should they be orthogonal or perpendicular to each other, the dot product will come out to the value of 0. Okay, so anytime you have a dot product of 0, that implies that the two vectors are orthogonal, which implies that they form a right angle. And for the first chunk of the notes for 3.3, in the videos I took you through a tour of how you could come up with some equations for certain objects, specifically equations for lines and planes based on a vector called a normal vector. So let me go ahead and kind of recap that. Let's say that we have a line, and this could be a line in 2 or 3 space, by the way. Every line and plane is going to have what's called a normal vector, which you could attach to the object, and should it be a normal vector, it's going to be perpendicular to the object in question. And the notation we typically use for a normal vector, no surprises here, is n. And so if n is perpendicular to the line, n can be considered a normal vector. And you could also have a normal vector for a plane. I'm going to sketch that out a little bit. Here's my plane. And you could attach a normal vector so that its initial point lies in the plane. And if it's a normal vector, we can assume that the vector is perpendicular to the plane, and we would use the same notation n for it. And so part of section 3 was going through certain equations that could be built based on either a point on a line or a point in the plane, as well as the object's corresponding perpendicular or aka normal vector. Then proceeded to take you through a couple of exercises in which you can determine based on normal vectors whether or not planes were parallel or perpendicular. And then we got to this idea of orthogonal projections, which is actually something that we'll revisit when we take care of what are called bases for Euclidean spaces and inner product spaces, but that won't be until chapter 6. What section 3.4 is all about is basically extending the set of equations that we could use to describe a line in n space or a plane. But the major difference between the equations we're going to work with in just a minute and those that were presented in section 3.3 is that they don't make use of a normal vector, but rather they make use of vectors that are either parallel to a line or vectors that lie in a plane, both objects of which we're trying to find equations for. And these actually give way to parametric equations and will ultimately be used to help us find what are called vector equations and parametric equations for a plane with very minimal information. So that's where we'll end it off today in 3.4. So let me go ahead and start with our first definition. Let's say that we have a vector x of 0 and a vector v, And we want to assume that the vector v is not the zero vector. And if you look in the diagram, x sub 0, not the Mortal Kombat character by the way, is given as a point on the line L, which of course, we could double that up as the terminal point of a vector that's connected to the origin. So that's why you're seeing the vector notation for what appears to be a point. But you'll notice that there's a line L going through the point x sub 0. And what we're supposed to glean from this diagram is that this line is parallel to this vector v that is connected to the origin. And so it would be in component form when it's provided to us in specific examples. So we define the line through x sub 0 that is parallel to that vector v in the following way. So what I want to point out is with this diagram, you're also seeing terminal point of a vector which has an initial point at x sub 0 and ending at this point x. And the way that we would figure out the components of this vector is by subtracting x minus x sub 0. Now I'm going to write that underneath this diagram, x minus x sub 0. Now assuming that this line is parallel to v, that would imply that this vector is parallel to it as well. What it does not imply, though, is that the vector x minus x sub 0 is the same length as this vector v. But the fact that it's parallel to the vector v would mean that it's at least a scalar multiple of it. Okay, remember, we can change lengths of vectors using scalars. So the vector x minus x sub 0 is equivalent to a scalar multiple of the vector v. And to get this vector equation, what we can do is add the vector notation x sub 0 over to the right-hand side. And we get the following. The vector x equals the vector x sub 0 plus a scalar multiple of the vector v. So tv. Okay. Now I'm going to kind of flesh out all the vectors involved here in component form, because when we write the vectors out in component form, it actually gives us a way of writing out parametric equations for each of the variables involved. So when we're in 2 space, this vector x, this generic x, is going to be an ordered pair, an order 2 tuple. And for that reason, we can write out the vector x in component form as x comma y. Now x sub 0, we could write that in component form as well. And just based on the notation, the coordinates involved, I'd like to write as x sub 0 comma y sub 0. And then plus the scalar t times a component form version of v, which I'm going to use the letters a and b. All right, everybody good? So now this gives way to parametric equations because what you could do on the right is distribute the parameter t, or the scalar, which I kind of gave it away. It's going to serve as a parameter in just a minute, and then combine the 2 vectors together. So we could write x sub 0 comma y sub 0 plus the vector ta comma tb. You could switch those around if you wanted to as well. But remember to add 2 vectors that are in component form. You add the corresponding components. So if we add the first component of each, we'd have x sub 0 plus ta, comma y sub 0 plus tb, and this is supposed to equal the vector with components x comma y. And I'll remind you of another fact, that if two vectors in component form are equal to each other, then the corresponding components have to equal each other. So what this all amounts to is that x is going to equal this expression, x sub 0 plus ta, or at, whichever, and y would be equal to this expression, y sub 0 plus tb, or bt, whichever you prefer. And these two equations would be parametric equations for the variables x and y. So that's one benefit of having a vector equation versus something like a point normal, like you saw in section 3. They can give way to parametric equations for all the variables involved in your vector x. Now, in the situation of a plane, you actually need one more vector in addition to the vector v. So you'll notice in the definition it says if x sub 0, v sub 1, and v sub 2 are vectors in n space. And this is kind of key here. v1 and v2 are not collinear. Okay, that means they don't lie along the same line. Then the plane through a point x sub 0 that is parallel to both v1 and v2 will have the following equation. Before I spill the deets on that, I would like to look at this diagram where we have a plane W, and in this plane there are a few things contained within it. The point x sub 0, the generic point x, the vector that can be formed by connecting x sub 0 with x, as well as scalar multiples of the two nonlinear vectors v1 and v2. Case in point, you have t1 v1 and t2 v2. And if you look closely, they're actually forming two sides of a parallelogram. So it appears as though this orange vector that I drew is actually the sum of the two vectors t2 v2 and t1 v1. So if we were to add these two pink vectors together using the parallelogram method, we would end up getting the orange vector, which we could actually write out the notation for this orange vector. It would be very similar to what we did in the diagram above. It would be x minus x sub 0. And so in a similar manner where we wrote x sub 0 on the other side of the equation, we could derive a formula for the vector x, which involves the three vectors x sub 0, v1, and v2. And here we go. It's going to be x equals x sub 0 plus t1 v1 plus t2 v2. Now this would give way to parametric equations as well. In a three-space situation, the vector x would be the ordered triple with generic coordinates x, y, and z. Generic coordinates for x sub 0 would be x sub 0, y sub 0, z sub 0, and then plus the scalar t1, which will double up as a parameter, times the components of v1, which I'm going to write as a sub 1, b sub 1, c sub 1, plus the other scalar, t sub 2, which doubles up as a parameter, times the components of v sub 2, which I'll call A sub 2, B sub 2, and C sub 2. And then you would just funnel everything down on the right-hand side until you get just one single order triple, in which case you could set each one of the variables in your vector x equal to the components. And what you would wind up getting as a parametric equation for x is x sub 0 plus t1a1 plus t2a2. For y, you would get y sub 0 plus t1b1 plus t2b2. And then for z, I'm sure you see it's coming a mile away, z sub 0 plus t1c1 plus t2c2. And those would be our parametric equations that we could get by virtue of this vector equation. Do you guys have any questions about any of these formulas? Okay, well, let's start putting them to use. In this first example, they want vector and parametric equations. So two things on the docket here, vector and parametric equations. And this is going to be for a line that contains this point P having coordinates 2, negative 1, and parallel to our vector V, which has components negative 4, negative 2. Now, if you were to connect this point P to the origin, you could actually consider the numbers 2 and negative 1 as components of a vector x sub 0. And we also have the vector that our line is supposed to be parallel to. So the reason why I'm mentioning that is because for the first part, numerically speaking, the vector equation is given as x equals x sub 0 plus tv. Now I'm going to leave the vector x as x, but on the right-hand side, I'm going to replace x sub 0 with its component form that we could create, 2, negative 1. And then to that, I'm going to add t, which will serve as our parameter for part 2. For now, it's a scalar, times the component form of v, which was provided, negative 4, negative 2. And that would entail the vector equation for this line. Do you guys want to go ahead and try part 2? Part 2 is for the parametric equations. All right, I've outlined how you can do that a little bit above on the page. So go ahead and give it a shot. And once about 30 seconds or so goes by, I'll jump back in and we can go over the results. All right, so I'll check in with you soon. All right, I'm going to go ahead and flesh out my details. Let me know how you line up. Okay, so how does the parametric equation for x of 2 minus 4t look to you folks? We getting 2 minus 4t for x and negative 1 minus 2t for y. Sweet. All right, very good. So I know this is all we need to provide, but if you're ever curious as to how this makes a line, you could make a table, a column for t, a column for x, a column for y, and then once you choose, some values of t, if you pop them into both the parametric equations here, you'll see that you can generate ordered pairs, and those ordered pairs would be ordered pairs for points on the line. And so you could, experiment with these parametric equations by choosing, random values of t, plugging them in, and you would get ordered pairs, and you could plot those in the plane, and you would see that when you're plotting those ordered pairs, eventually they take on the shape of a line. So I'll leave that up to you guys if that's something you want to do on your own, and if you have any issues with that, I'll be happy to help you. But I'd like to move on to the second example. So P of 2, negative 1 can be doubled up as a vector. Yeah, so let me show you how that works. So the notation, P of 2, negative 1, that's definitely like some good old-fashioned geometry notation where it's just the coordinates of a point. And I'll go ahead and plot that point. There's P. We can double this up as the terminal point of a vector that's connected at the origin. And so if we wanted to, we could put a point at the origin and create a vector which connects the origin to this point P. And this vector that I just drew, I'm going to write it as x sub 0. And since it's in component form, and its terminal point has the coordinates 2, negative 1, then these numbers 2, negative 1 would serve as the components of x sub 0. And so, notationally, it looks a little bit different than vector notation, but we could always connect a vector from the origin to whatever point they give us to form a vector that's in component form. And the coordinates 2, negative 1 double up as the coordinates of the terminal point of x sub 0. So it's not really given to us as a vector, but using this argument, we could convert it to one if we wanted to. And that's actually what we kind of did behind the scenes to get x sub 0. Does that make sense?
Right. So x sub 0 is the vector that starts at the origin and goes through point 2, negative 1?
Yep.
Okay. Does it end at 2, negative 1, or does it continue past it? Is that a terminal point, or it doesn't matter?
Well, yeah, it does matter. So if we want 2, negative 1 to be the components of the vector x sub 0, then 2, negative 1 is where x sub 0 needs to stop. Because remember, when a vector is in component form, the components of the vector tell you where the terminal point is at.
Okay. Thank you.
Yep. So for this upcoming example, or this next example here, same instructions, but this time we want a plane. And maybe I'll kick it off to you folks to try your hat at it. So very similar process as the last example. They provide us a point 0, 6, negative 2, which can be converted to the components of a vector connected at the origin. So kind of like what we did in the last example, this could double up as the terminal point of a vector x sub 0 that's in component form. And then we have two vectors, v sub 1 and v sub 2. So I'm going to give you guys a few minutes to work on this. Okay, keep in mind there are two parts, vector equation as well as parametric equations. All right, I'll check in with you folks in a few. All right, I'm going to write out my answer to part 1. So this is based on the equation on the last page, the vector equation, with these particular vectors subbed in their component form. And that's really all you would have to do to come up with the vector form of the equation. So I have confirmation on this result. We'll rock on. Now for the parametric equations, this one we got to get some elbow grease on. So what I'm going to do is first rewrite the vector x on the left as an ordered triple, generic coordinates x, y, and z. And on the right-hand side, I'm going to distribute in these scalars, which will double up as parameters. 0, 6, negative 2, nothing to do with that for right now. But this is going to be added to 0, 9, T1, negative T1, and added to negative T2, 3, T2, and T2 as well. And we can continue on the right-hand side by combining all the corresponding components. So you would add together the first component of each vector, and you can do that all at one time if you're comfortable with it. So 0 plus negative T2 would give us negative T2. Then we'd have 6 plus 9T1 plus 3T2. And then the third component of each, negative 2 minus T1 plus T2. We're not quite finished because we still need to set the components of our left vector and right vector. We need to set those components together, equal to each other. So we'll set x equal to the first component of our vector on the right, which is simply negative T2. So x equals negative T2. Y would equal the expression in the second component. And then z would equal that very last component's expression. And these would be the parametric equations. And you could experiment with these, much like with the last example, by choosing not only a value of one parameter. Keep in mind we've got two parameters here now. We've got T1 and T2, so you would have to make a column for each of those parameters. And as soon as you choose values for T1 and T2, remember you can choose any real number. They don't have to be the same. You're going to generate an ordered triple. And the more ordered triples you have in plot, which is admittedly not the easiest thing, you would see that you could form a plane after a certain amount of points are plotted. But we'll actually forego that. But before I move on to the next example, are these the parametric equations that you folks are coming up with too? Okay. Yep, go ahead.
Just a quick question. If you were to go to like 4 space, would you end up having 3 parameters? So T1, T2, and T3? Is that like, would it keep adding more parameters the higher up you go?
So yes, it kind of follows that natural progression, right? And the reason for that is because these vectors are vectors that are parallel to an object in that particular space. So with a line, you only need one vector, to generate the equation for the line. So essentially, these are equations that are based on like parallel objects. In the line situation, you would only need one parallel object, and that object is obviously going to be a vector. So you would only need one vector in order to come up with the equation for the line L, which by the way is a one-dimensional object, right? A line. If you look at the plane situation, a plane is a two-dimensional object, and so you would need two vectors in order to generate a two-dimensional object. And the two vectors, v1 and v2, can be thought to be placed within that plane. And if we were to move up to 4 space, then our object would progress to a three-dimensional object that we would need vectors in. And so in order to create a three-dimensional object, you would need three vectors, right? Because if you only had two, then you could only create a plane, which is a two-dimensional object. So yeah, you would need vectors v1, v2, and v3, in addition to a third parameter, p sub 3. So you could kind of argue the progression of these vector equations based on the dimension of the object that you're using to generate them, right? So in a line situation, a line is one-dimensional. Okay, so that's going to only need one vector. For a plane, okay, that's two-dimensional. So in order to create a two-dimensional object, we would need two vectors, v1 and v2, and then it just kind of goes up in dimension from there on forward. No problem. Telling you, we take it to higher levels in this course, right? Did I mention that one before? I'm just kidding. All right, our last example kind of reminds me of an observation that a lot of students in graduate mathematics courses eventually stumble upon. Like the shorter the problem, the harder it can become. So for example, think about the Pythagorean theorem, all right, a squared plus b squared equals c squared. That's an example of something called the Diophantine equation, and people wondered if you increase the powers to threes instead of twos, would we be able to come up with integer solutions to that? So for example, they were looking at things like x to the n plus y to the n equals z to the n, and the problem is really easily stated. Are there integer solutions for x, y, and z that are not the obvious ones when the value of n is greater than or equal to 3? So for example, could we come up with values of x, y, and z that satisfy this equation other than something like 0, 1, and 1, or 1, 0, and 1, or 0, 0, 0? Like, could we come up with some numbers that are different from those that would satisfy this? And so the question generalized, okay, so if it works for a power of 2, does it work for a power of 3, power of 4, so on and so forth? And this gave way to something called Fermat's theorem. And it wasn't really it wasn't really a theorem at the time. This mathematician, which actually has some number theory results that tie into cryptography, but it wasn't necessarily a theorem at this time that he pondered this. As legend goes, he said that his statement or conjecture regarding this kind of problem was true, but he didn't have enough space in the margins of his paper or his book. He didn't have enough space to write its proof out. So if you have some time, you should look up Fermat's theorem. His claim eventually did get proven by, I think, an English mathematician, Andrew Wiles, and I think it took him something along the lines like 13 years to prove it. But yeah, it's an example of one of those very briefly stated problems that ended up being a lot longer than you would expect in terms of the solution. It's not going to be a 13-year-long problem for us with this example, but there's a little bit of work involved with something like this. So I want to show you guys how you can iron it all out. Same instructions, but we're kind of provided a different set of conditions. We want to find vector and parametric equations for a plane It passes through the origin, which, let me remind you of what the origin is in 3 space. It's really no surprise, I'm sure. 0, 0, 0. But is orthogonal to a vector, which we're going to assume this is a vector in component form, has components 3, 0, and -2. Oops. Well, let's see if we can get a visual of this. So over to the side, I'm going to sketch out my representation of a plane. And the plane has to be going through the origin. So what that means in terms of my diagram is I'm going to put a point in this plane and just write out the ordered trip associated with the origin. And what we can do is actually reimagine this ordered triple as the terminal point of a vector, x sub 0. In other words, we can convert the origin to our vector x sub 0 that we'll need for our vector equation. Now what do we do with this information where it says it's orthogonal to 3, 0, -2? Well, remember, orthogonal means that it's perpendicular. Okay, so our plane has to be perpendicular to a vector having these components. So what I'm going to do is I'm going to attach a vector to this plane, but I have to draw it in such a way that it's orthogonal to it. And the way to go about doing that is to put its initial point in the plane, and then you can draw an arrow going out of the plane and indicate to yourself that this arrow or vector is going to be perpendicular to our plane. And this is really an example of a normal vector to this plane that's going through the origin. So you can actually write the components 3, 0, -2 or indicate them as a normal vector n. Okay, so does this make sense so far? In order for our vector to be orthogonal to the plane, it has to be perpendicular to it. And we can reorient this vector so that its initial point is in the plane, in which case we can convert it to a normal vector. Is that all making sense so far? All right, so before we add more to this plane, keep in mind that the vector equation for a plane goes x equals x sub 0 plus t1 v1 plus t2 v2. Now we already know what we can use for x sub 0. Okay, we can use the origin as x sub 0. But we have to remember something special about the vectors v1 and v2. Okay, the vectors v1 and v2, these guys have to lie in the plane. So here's what I'm going to do. I'm going to draw a vector in this plane, and I'm going to call it v1. And v2 has to be in the plane as well, but based on the definition of the vector equation for a plane, v1 and v2 cannot be linear, or collinear, that is. Okay, so what that means is when I draw a v2, it has to have a little bit of a different direction than v1. So what I'm going to do is I'm going to attach v2 to v1 and just draw it going in a different direction, and that'll be our v2. Now, here's really the crux of the problem. We have to figure out what the components of v1 and v2 are going to be and I'll let you know in advance that there are many possible coordinates for those two vectors. But regardless of which numbers you use, we still have to keep in mind that there's this normal vector n, which is perpendicular to the plane. And I'm going to make a connection between all three vectors, all right? Since n is perpendicular to the plane, it would imply that the vector n is perpendicular to both the vectors v1 and v2, since they're in the plane itself. Long story short, if we took the vector n and we dotted it with the vector v1, what number should I get after that? 0. Yep. And the same thing should happen with the dot product of the vector n and v2. That should be 0 as well. So keep in mind, yep, so the vector n is perpendicular to the plane. And if the vectors v1 and v2 are in the plane itself, the vector n has to be perpendicular to v1 and v2. Yeah, and so, based on the geometry of those vectors, the dot product between n and the vectors v1 and v2, the dot product has to be 0. So that's the definition of what it means for vectors to be orthogonal, is that their dot product is 0. Now with that in mind, I'm going to write out the components of all these vectors. We have 3, 0, and -2 for n. And we don't know what to use as the components for v1, at least not yet. So I'm just going to write them out generically. a1, b1, and c1 equals 0. And then based on the second dot product equation, 3, 0, -2 gets dotted with a2, b2, and c2. There is going to be more of a quote-unquote scientific way of figuring out the values of a1, b1, c1, and so on and so forth when we discuss the cross product tomorrow. But for now, it's kind of a guessing check scenario. Okay, we need to come up with values for the components of v1 such that the dot product would come out to be 0. So one possible combination of numbers for a1, b1, and c1 would be 2, 0, and 3. And to see that this works, or to check it, we'll carry out the dot product. And I'll use the alternative form of the dot product, where we multiply corresponding components and add them together. So if we carry out the dot product calculation on the left, we'd have 3 times 2 plus 0 times 0 plus -2 times 3. And we'd want to check to see if that dot product comes out to be 0. And I believe it does, because this is 6 plus 0 minus 6 on the left. In other words, we get 0 equals 0. So we can actually use these components as the components of the vector v1. Can anybody come up with a different set of components that we could use for v2? And then we'll check it. So the issue with 406 is that it's a scalar multiple of our vector v1. Now, what does that mean? What it would mean is that the vectors v1 and v2 in this case are collinear. I think it's 2 L's. or maybe it's 1L, but either way, we want to be sure that our vector v2 is not collinear with the vector v1. And if we use a scalar multiple of v1, all it really does is change the length of v1, so v2 would be in line with v1. So I would try something else. I remember v1 and v2 cannot be the zero vector. They have to be non-zero vectors, right? So Friesta, what do you mean by the same as the first one? 2, 0, and 3. So if we use 2, 0, and 3 as our vector v2, then that would be another situation in which case v1 and v2 are collinear. So we have to avoid this. Let me see if I can draw it out. Let's say this is v1. We have to avoid v2 being collinear with v1. And so we can't really use a scalar multiple of v1 to get v2. So I'm going to do like they used to do on smoking heads. I'll just draw a little, no smoking of the vectors v1 and v2.
But,
no collinear vectors.
Would 1/3, 0, and 1/2 work? Or
1/3, 0, and 1/2, as long as it's not a scalar multiple of v1, I think it would be okay to use that. Let's check it. So you said 1/3, 0, and 1/2?
Yeah.
Okay. Would this be a scalar multiple of the vector 2, 0, and 3?
That's what I'm trying to think of.
Now you could actually distribute the scalar in and set the components equal. And if you get the same value for k, then it is a scalar multiple. So, if you solve for k in each equation, you get 1/6 in the first one, and you get 1/6 in the second one. So it turns out that this vector you gave is actually a scalar multiple of the first one.
Okay.
All right, guys, don't virtually throw anything at me, but you could actually use 0, 1, 0 as the components of v2. Can you see why?
Yeah, I see it now, man.
So if you were to dot product these two, you would have 3 times 0 plus 0 times 1 plus -2 times 0. Now the vector 0, 1, 0 is not the zero vector. Okay, so that condition is satisfied. And if you compare the second component of each of these two vectors, v1 and v2, that kind of gives you the sense that they're pointing in different directions. Think about plotting these points in 3 space. 2, 0, 3 would be in the xz plane. 0, 1, 0 would be in the xy plane. All right, but like I said, in the next section, we'll actually have a scientific way of coming up with these vectors v1 and v2. But at this stage in the game, it is kind of a guessing check sort of ordeal. These aren't the only vectors v1 and v2 that would meet the criterion, but these are typically the first that come to mind, over the years. So the problem isn't fully finished, but we are out of time. So what I'm going to do is draft up the rest of the solution to this problem and include it in the uploads in Blackboard. But before I let you guys go, do you have any questions for me?